To explain the operation of the artificial horizon a little more, I'm going to now discuss the indications that a pilot will see during level flight, climbing and descending. And to assist with that, I have attached the artificial horizon to my Skywatcher as GTI mount, which is controlled via the SynScan Pro app on the iPad. Now, to help you visualize what the aircraft is actually doing, I have placed a small model aircraft on top. And this is a model of a Global Express XRS, which is the type of jet that I fly. And I should really point out that it's actually called a Global Express because it's designed to fly around the globe. It's not called the Flat Earth Express. I just thought I'd throw that in there. But looking at the operation of the artificial horizon, in level flight, what we're going to see is that type of indication. You'll see that the wings are level and the pitch dot on the instrument is in line with the horizon behind it. The blue represents the sky and the brown represents the ground, obviously. So when we pitch the aircraft, we're going to see a different indication. Now, I just want to point out in the app that we can accurately measure the degree of pitch up and pitch down. Now, we need to look there at azimuth and altitude. It's this number here specifically that we're interested in. So let's take a look at a climb. So the first thing I will do is put the aircraft into a climb, and you will see the model aircraft pitching nose up, and you will see the corresponding indication on the artificial horizon. As the aircraft pitches up, the horizon will appear to drop in the display, and that will put the pitch dot and the wings clearly in the blue part of the display. What I'll do initially is just pitch up to about 15 degrees, which is roughly the pitch attitude that we would have when taking off at maximum weight. So the aircraft is pitching up, and I'll just fine tune it. That's 15 degrees, you can see just there, and that's roughly what it looks like. You can see the aircraft has adjusted its attitude so that it's in the climb, and we can now see the indication in the artificial horizon. As described, we've got the pitch dot and the wings clearly in the blue part of the display. Now, that indication will not change. Remember, the instrument is correcting to true level, and as long as the case of the instrument is angled away from true level, it's going to show an indication like that. So I could leave this here for an hour. It's not going to change in its display. The instrument is correcting to true level. It's always going to show accurately a climb. Now, I'll just increase that climb up to 25 degrees. That's personally the most I've ever seen in this model aircraft. When we're operating at light weights, that's about 25 degrees there. Operating at light weights, we can very easily climb with a 25 degree nose up attitude to prevent the aircraft from overspeeding, and we can be indicating 300 knots, climbing at a severe angle like that, and at very light weights it's got the performance to just keep going up. And that's the indication you will see in the artificial horizon, and again it will stay like that for the duration of the climb. So let's just go back to level. The easiest way to do that is just return to a stored home position. So there's our level flight indication again. Okay, let's try pitching down. Now, you don't really pitch down that much in the course of a normal flight. In fact, no more than about 5 degrees. But what I'll do is I'll pitch down to about 30 degrees nose down, simply to demonstrate the indication of the instrument. Okay, so that's now showing a 30 degree nose down attitude. As you can see, it's quite extreme, and you'd probably have a lot of terrified passengers if you ever did that in a normal flight. But once again, take a look at the indication. We can see that the pitch dot and the wings are now clearly in the brown part of the horizon display. And again, that's just going to stay there for as long as we hold that descent. The unit will not correct back to a level indication. It's always going to show a correct climb or a descent. The only time it will show level is when we actually return to level. So let's do that now. And there's our level indication again. So let's take a look at another concept. So I just want to touch briefly on the way turns are conducted when pilots are flying aircraft under the instrument flight rules, which is basically any airline flight you will go on is operated under the IFR. But obviously they're not just going to throw the aircraft around randomly and fly aerobatic maneuvers. Everything in instrument flying is about keeping the aircraft safe, and that means maintaining it within protected airspace. Now, this is a series of instrument approach and departure charts, and this is for Sydney Airport, and each of these charts are predicated on the performance of the aircraft and that the pilot will fly standard rate turns. Okay, now if the pilot does that and stays within the speed limits, then we are ensured of maintaining the aircraft within the protected airspace. And what I mean by protected airspace is that it has been surveyed and there are no ground obstacles that will infringe the likely flight path, whether it be on a departure or an arrival. So that's the instrument approach chart. The type of turns that we use, this document relates to instrument approaches. The type of turns that we use are all standard rate turns. So let's have a look at what that means. It's called a rate 1 turn, and it means we are changing direction at the rate of 3 degrees per second. That equates to 1 minute for a 180 degree turn and 2 minutes for a 360 degree turn. Now, in the aircraft, our turn coordinator can help us do that, because if we are turning and we match the wings to the white indication there, we know that we will be completing one turn of 360 degrees in 2 minutes. And in fact, many turn coordinators actually label 2 minutes. That's telling me that it's a standard turn coordinator that will indicate a rate 1 turn quite comfortably. So the standard rate turn, you can look it up in Wikipedia. It gives you a bit more information about it, and there's lots of information on Google if you also do a search for rate 1 turn. So again, let's just come back to this and let's have a look at how pilots can actually know that they are flying a rate 1 turn. We looked at the turn coordinator, but we also have a rule of thumb, and that rule of thumb is to turn with an angle of bank which is 15% of the true airspeed. Okay, now that's not as complex as it might sound, because if we're flying at 100 knots, 15% of that is 15 degrees angle of bank. If we're flying at 200 knots, 15% of that, 10% of it is 20, 5% of it is 10, so there's 30 degrees angle of bank. So they're your basic rule of thumb figures. If we're flying at 150 knots, we would use an angle of bank of 22.5 degrees. So the rate 1 turn is used by pilots everywhere around the world. It ensures that we keep the aircraft within the protected airspace, and really we're not going to be using any turn rates more severe than that during the course of a normal flight. So how does that relate to our artificial horizon? Well, the artificial horizon needs to be able to maintain an accurate indication even if the aircraft is maneuvering. So what we need to look at is whether the artificial horizon can actually give us reliable indication, and can it correct even if the aircraft is maneuvering at rate 1. So clearly, while we're on the ground, we cannot accurately represent the forces being experienced by this artificial horizon in flight in an aircraft. There's no way of doing that while we're on the ground, because in the aircraft it will be turning and we will be experiencing changes in the direction and the value of the g-force. So this demonstration is not attempting to recreate the forces it would be experiencing in an aircraft. Consider it a standalone demonstration that the artificial horizon is capable of correcting itself back to level even when it is being rotated. So what I'm going to do is introduce an error and then rotate the mount 360 degrees clockwise several times, and we will see how long it takes to correct the error. Then we will repeat the experiment going in the opposite direction. I am fully acknowledging once again this is not attempting to recreate what we see in an aircraft precisely. It's a standalone demonstration. I may do this in the future in an aircraft. I'm considering going and getting current again on a light aircraft. It's simply a matter of going and doing a quick check ride with one of the flying school instructors to cover their insurance requirements, and then after that there's plenty of experiments I could do in a small aerobatic light aircraft. So no promises, but it is just something I'm considering as an option. So let's take a look at this demonstration, which is a standalone demonstration showing you that the artificial horizon is more than capable of correcting errors while it is being rotated. So looking at the app again, we can adjust the rate of slewing by adjusting this number here. At the moment it's on 8, which is the second fastest rate, and that causes the mount to slew at a rate of 2.5 degrees per second, which is slightly slower than the standard rate of 3 degrees per second. Now, if we go to position 9, it is actually moving faster than a rate 1 turn. So we will actually use that, and I'll demonstrate that the gyroscope is perfectly capable of leveling itself back to true level even while the gyroscope is being rotated at more than a rate 1 turn. So what I will do now is intentionally introduce a 10-degree pitch error, and I will do that by climbing the aircraft to 10 degrees, recaging the gyro, releasing the cage, and then returning the gyro back to level. You will see the error in the pitch, and then we will rotate the mount 360 degrees and just keep it rotating at faster than rate 1, and you will see that the gyro is perfectly capable of restoring itself back to true level while it is being rotated. So the first thing we want to do is pitch the nose up. Okay, it's about 11 degrees, that's close enough. You can see the aircraft is climbing, and there's our climb indication. I'll just get this app ready for the return to level, and let's cage the instrument. Okay, so it's now caged. I'm going to release the cage and return the unit back to level. So there you can see, even though the aircraft is level, it is showing a false indication of a descent. So what I'm going to do now is just let the aircraft, or let the mount rotate continuously 360 degrees, and you will see that after several rotations it will have corrected itself. I was just having finger trouble then with the app. It had disconnected from the Wi-Fi on the mount, but it's reconnected now. And I'll just put the mount down, I'll put the camera down I should say, so that I can swap hands and so that I can make sure the cables don't bind. But as you can see, it's all happening in real time. Just repositioning the cables so they don't tangle. And there's our gyro. You can see it has already made a lot of that correction. By the time it goes around another circuit, it should be virtually back to the starting position. So the rotation is about 3.5 degrees per second. It's faster than a rate 1 turn. So as the instrument comes around again, you can see that it has actually now corrected that pitch error. So it's more than capable of correcting itself even while the unit is being turned. So we will now repeat the exercise going in the opposite direction, and when I hit the home position on the app, the mount will rotate twice because we rotated clockwise twice, so now it will basically unwind itself to get back to the home position. So let's introduce the error first. Pitching the aircraft up, recaging the instrument, releasing the cage, pitching back down to level, okay, there it is. You can see the deliberate pitch error that we have introduced, and now I'm just going to make the unit return to home. And you can see immediately as it starts to turn, we are seeing a degree of roll occur. Now that is one of the turning and acceleration errors that can be present in an artificial horizon, but you'll see after 2 rotations it should have corrected itself back to level. Now I realize this is not simulating how the instrument would be operating in an aircraft, because an aircraft will be also banking, and we will also have centrifugal force which will be causing the apparent G to be in a different direction. So please, no need to comment on the channel that this is not how it would occur in an aircraft. I realize that fully. This is a demonstration that the gyro can self-erect while it is being rotated. If I get the opportunity to test it on an aircraft, I will certainly do so. I understand fully that this is not exactly what would be occurring on an aircraft, so please, no need to mention that. And you can see that after 1 rotation, some of that error has now been corrected. I'm planning a few different experiments also, and I've thought of a way to configure this mount so that I will be able to introduce roll and pitch on the artificial horizon. My experiments are always a work in progress. This one today is simply to show you that the artificial horizon can self-correct while it is being rotated. Okay, there's still a small amount of error, so we'll just keep that rotation going around another turn. So it's just taking a bit longer going this way. And there you can see, third time's a charm. The horizon has corrected itself nicely. So there's the unit back at the home position and nicely level. What I will do this time is another demonstration of how the unit can still correct itself back to level even if the aircraft is moving around, if it's pitching up and down in turbulence, and we're getting a bit of left and right movement as well. So let me just again introduce that error. We will recage the instrument. There it is. Releasing the cage, leveling the instrument, and you can see we have that 10-degree pitch error. Now what I'm going to do is just via the app, just do random movements up and down, just like that, left and right, combination movements, turning and pitching, and we'll just do that for a couple of minutes. And after a few minutes I'll hit the home position and we can see if the gyro has been able to correct itself even while it is continually being moved in two different axes. Okay, I'll just go back to the home position momentarily. and we'll see how close it is to having corrected itself. Okay, most of the correction has occurred, but obviously it just still needs a little more time. So we'll just keep maneuvering. And again, I realize this is not exactly how it's going to occur on an aircraft, because there are no changes in the value of G. In an aircraft, you're going to feel G when you're turning, but this is simply demonstrating that the gyro will still correct back to level when it is being moved about 2 axes during the correction process. And yes, I will repeat this in the future, adjusting the roll and the pitch axis instead of just the yaw axis. And if I can work out a way to do all 3 at once, I certainly will. So there's no need to point out the flaws in the fact that this is not a real representation of the aircraft. I know that fully, and when I get a chance to do it in an aircraft, I will do so. This is a standalone demonstration of the gyro's ability to correct itself while it is constantly being moved in 2 axes. Okay, that looks like it's pretty close. So let's hit the home position and see how good it is. Okay, so you can see the gyro has corrected itself back to level, even though it was constantly being moved in pitch and yaw. I think that's fairly self-evident that even if the unit is moving, it is perfectly capable of correcting itself back to level.